It is the first day of the week of my first midterm. Am I going to get through? I don't have much time, so we need to go fast. So let's say we have a vector. We can take the derivative of that vector by taking the derivative of its component parts. We can do the same thing with a parametric line. The derivative of a parametric line is going to be the derivative of its component parts. The same logic applies for limits along parametric lines. The same logic applies for integrals along parametric lines. If we're given a parametric curve, we can find the unit vector that is tangent to a point on that curve by using this equation. It's going to be the derivative of that parametric curve over the magnitude of the derivative. We can also find the velocity at a certain point on the curve by finding the magnitude of the derivative at that point. We can also find the vector that is normal to that point on the curve by taking the derivative of the tangent unit vector and dividing it by the tangent unit vector's derivative's magnitude. Curvature is a measure of how curvy a curve is. It is a value given by the magnitude of the tangent unit vector divided by the magnitude of the derivative. Or it's also given by the cross product of the original parametric curve's first derivative and the original parametric curve's second derivative, the magnitude of that divided by the magnitude cubed of the first derivative of the parametric curve. Now all these values are going to very quickly become useful because the equation for acceleration along any t of a parametric curve is going to be given by the acceleration in the tangential direction times the unit tangent vector, plus the acceleration in the normal direction times the normal vector. So as you can see, along any point on this curve, there's going to be an acceleration in the tangent direction and an acceleration in the normal direction. And that's what we're concerned about. Now, the acceleration in the tangent direction is relatively easy to find. It is simply the derivative of the velocity equation or the double derivative of the position equation. The acceleration in the normal direction is a little bit trickier to find because it is the curvature times the velocity squared. Now we recall that the curvature is given by the magnitude of the cross of r prime of t and r double prime of t divided by the magnitude of r prime of t cubed. And we also recall that the velocity is a scalar given by the magnitude of the velocity equation. So we finally get that the acceleration in the normal direction is given by the magnitude of the cross of r prime of t and r double prime of t over the magnitude of rt cubed times, I got that wrong. Sorry. This is supposed to be squared, not cubed. So, we finally get that the acceleration in the normal direction is given by the magnitude of r prime of t cross r double prime of t over the magnitude of r prime of t cubed times r prime of t squared. So, we finally get that the acceleration at a certain point t on the parametric curve is going to be given by r double prime of t times the unit tangent vector plus r prime of t cross r double prime of t, the magnitude of that, over the magnitude of r double prime of t times the normal vector, normal unit vector. That is. I misspoke. It isn't divided by the magnitude of r double prime of t, it's divided by the magnitude of r prime of t. Alright, I can't keep skimping out on studying Gauss's law. I need to get that done tonight. Continuous charge distributions over areas will just have to wait for another day. Electric flux is generated when electric field lines pass through an object. It is given by the dot product of the electric field vector and the area vector. For any arbitrary surface, electric flux is defined as the integral of the product of the electric field vector and the change in area, dA. So from this information, there are two extremely powerful relations that we can derive. But first, there are a few assumptions that we need to make. In order for us to be able to use Gauss's law in the way that we are going to, the object that we are going to be using Gauss's law on must be A, closed, so it can't have any defining edges, so it can be a plane of infinite size or a line of infinite length, or even just a sphere. Secondly, the objects that we are going to be using must have an extremely high level of symmetry, so they cannot be asymmetrical in any way, shape, or form. So the first part of Gauss's law does not need to comply with both of these, it only needs to be a closed surface. So if we draw electric field lines from this point charge through the object, we notice that every single field line that enters the object also exits the object. So any point charge outside of a closed object generates zero electric flux, which is why this section of Gauss's law is defined by the charge inside the closed object. But this is only the first part of Gauss's law. So what we're trying to do now is we are trying to find electric fields on volumes using Gauss's law. So let's remember that we get the maximum amount of electric flux when the area vector and the electric field vector are parallel. So when the area that we're looking at is perpendicular to the electric field lines. So let's examine three different cases. Now if we want to use Gauss's law to examine the electric field generated by the point charge inside of a sphere, we can. Because a sphere is of course closed, and since the point charge is placed in the middle, the system is highly symmetrical. If we have a plane of infinite size, it is symmetrical, but we also count it as closed, since very technically, that plane has no boundaries by which we define it. The same thing goes for a line. It is obviously symmetrical, but it is also boundless, because of its infinite length. So for the plane and the line, we use cylinders to examine. So as you can see, the electric field lines on the surface of these Gaussians are normal to the surfaces at the points they intersect. So, based off of that, we can define something really, really cool. So we already know that the flux in an object is equal to the integral of the dot product of the electric field vectors and the area vectors. But we're going to make this thing a closed integral. Now here's what we can do. Now since this thing is symmetrical, we know that the electric field lines are going to be equal everywhere. So there is no change in the electric field. And since this thing is boundless, we know that the area is going to be constant. Wait, what? We also know that our Gaussians are going to be determined by set geometric principles. For example, the surface area of a sphere, of a cylinder, of a circle. So we can also pull the dA out of the integral, since there is going to be no change in area. So that means that our electric flux is going to be equal to the electric field times A. Now we also know from our previous part of Gauss's law that our flux is also equal to the Q inside of the volume over epsilon naught. So we can set these two values equal to each other. And this means that by using Gaussians, we can find that our electric field is equal to the Q inside times area over epsilon naught. Isn't that awesome? So, I know that I'm going to need to do a few more examples with this, but I feel like I have a pretty good understanding of it, which I'm very, very, very happy about, especially considering how tenuous my knowledge of it was this weekend. But, I'm about to get kicked out of the room in like 5 minutes, so I think that is where I'm going to end it tonight. Thank you so much for watching. See you tomorrow.